consider from just a two-level system last time. Okay, so let me repeat. I will consider a two-level system. Let's assume your two-level system is described by the ground state, or one of the levels is described by state 1 and another level is described by state 2. Okay. So let's say the energy here is unperturbed energy. Okay, so I'll call this as E10, and the unperturbed energy of this very state is E20. Clear? Okay. So let's write the unperturbed Hamiltonian. So that I will write as E10 1 okay, plus E20 2. Okay? So in the matrix form, this can be written as E10 okay, 0 0. Okay? So let's add the perturbation to this very system. So let me write the perturbation as some lambda. Okay. So let me write this way some. Okay. So let me write some V1 2 plus V star 2 1. So what is the perturbation? So look here. So it is simply the off diagonal terms. If you look here in the matrix form, it is 0. So you are having V star and 0. V is the strength of the perturbation. It's you can think this two-level atom is in some external field, okay? And V is the strength of that field. Okay, so what it will do, it will simply make the this perturbation will simply make the transition from the level 2 to level 1 and level 1 to level 2. So there is a so this kind of perturbation will simply give you the transitions from this level to this level or this level to this level. So in this unperturbed Hamiltonian, there are no transitions at all. Clear? Okay, so I can write the total Hamiltonian now like this way as 0 plus lambda h1. Okay, so what is that equal to? Okay, so you can write it this way: E10 1 1.
Hello. Slow.
So, okay. So where I was? Okay. So you are having E10 1 1. Then I am having this E20 2 2. Okay. So then you can write this lambda V12. Okay. So you are having then lambda V star 2 okay 2 1. Okay, so let's forget about everything. So if you are having a general two-level system, okay, any two-level system which has having okay where the energy levels are specified and the transitions from one level to the another level is specified. Clear? So this is the general two-level system. Okay. A Hamiltonian for a general two-level system. Put lambda equal to 1. Forget about everything. Put lambda equal to 1. Clear? So this will be the general two-level system. Okay. So you can write it in this fashion. Okay. E10. So then you are having V star. Okay. So let me put lambda because we are lambda is our control parameter. Okay. So this is your total Hamiltonian. So any 2 by 2 matrix, a Hermitian 2 by 2 matrix will represent your two-level system. It should be Hermitian. Clear? Okay. So okay. So in order to figure out what we need to figure out. Okay. So I am giving you a matrix. What is something which we require? These are the eigenvalues of the matrix. So let's okay. So this matrix represents our Hamiltonian. If I know the eigenvalues of this matrix, so I know the eigenenergies. Clear? So if I know the eigenenergy, so then I can know actually what is the effect of this very perturbation. Is it? So you can apply the perturbation theory what we have developed so far, okay, directly. But we will not do that. full machinery. We will simply try to diagonalize this Hamiltonian. If I know the, okay, so the eigenvalues of this very matrix, I know then how the energy levels are shifted. Clear? So you start with this thing and you apply this thing, okay, this of these off diagonal terms. So then you can say, okay, so you can see these energy eigenvalues will depend on what? This lambda, on this control parameter. Clear? Okay, so let's try to diagonalize it. Okay, so how to do it? So now let's try to diagonalize it. Clear? Okay, so our lambda is very small quantity. Okay, let's diagonalize it. Now tell me how to diagonalize it. So you make a characteristic equation. Let's say if you are having a matrix A, B, C. Okay, so let me write B star and C. This is a matrix. Clear? Okay, and I want you to diagonalize it. What you do? You form a characteristic equation. How is that? So you put actually this determinant of this objective A minus lambda B, B star C minus lambda, that's equal to 0. Clear? So this is actually the characteristic equation. From here you will get, okay, you are having a 2 by 2 matrix. So from this characteristic equation you will get a quadratic equation. Clear? If it is, let's say, n by n equation, you will get a nth order equation. Clear? Okay. So how many roots are possible now? 2 roots. So you simply write it as A minus lambda and C minus lambda, okay, minus magnitude of B square, that's equal to 0. Clear? Okay, so now solve this very equation, you will get roots of the equation. Okay? So now let's solve this thing. Okay, so let's solve it. So now tell me what will be the, so let me write the eigenvalues to be E plus minus. So those will be equal to, so if you can calculate it, E1 0 plus E2 0 divided by 2 plus minus. Okay? Anybody? Anybody? So then it will be, yes, root of, so it will be sum. Okay, so let's calculate it. So let's calculate it for your paper. So it will be something E1 0 minus lambda into E2 0 minus lambda, okay, minus lambda square mod V square, that's equal to 0. So you are having lambda square. So this is your characteristic equation. E1 0 plus E2 0, okay, then you are having plus E1 0 E2 0 minus lambda mod of V square equal to 0. So let's write the lambda. So that is equal to minus B. So minus is already E1 0 plus E2 0 plus minus root of B square. So it is E1 0 plus E2 0 square, minus 4AC. A is 1, C is this objective. So that is E1 0 E2 0 plus 4 lambda mod of V square divided by 2A. Clear? So now you are having E1 0 square plus E2 0 square minus 4 thing. It will be simply these two terms combined. It will be simply E1 minus E2 whole square. Clear? So therefore you are having here, so 1 by 2 root of E1 naught, okay, minus E2 naught, okay, whole square, then plus 4 lambda mod of V square. Okay, since lambda is our control parameter, clear? So we can expand this objective in powers of lambda. So this is a square root of, let's say, 1 plus x square, and you compute the square root in powers of x. Clear? Got it? Okay, so let's take this factor out. Okay, let's take this out. So it will be simply equal to E1 0 E2 0 by 2 plus minus, so it will be something E1 naught minus E2 naught, okay, divided by 2. Huh? So if I take, let's say, so it is something root of 1 plus, let me write lambda mod of v square. So 1, so I will put it like this. E1, let me write it. So there is a lambda square, huh? Not lambda. It's a lambda square. Huh? E1 naught minus E2 naught. Okay? So no, like this. I have taken this 4, I can write 1 by 2. There is a reason for it. Yeah? Okay? Can I write it?
Yes.
Now look here, how to expand it. Now the point is that you are having a square root of something. I don't know whether, okay, so this can be complex, this can be real, whatsoever. Huh? Okay? So how I can expand this square root of 1 plus x square, provided this square root converges. Clear? So you are having this kind of situation at hand. Now look here. So you are having a function, let's say f of z, root of 1 plus z square. Clear? So this is a function and you need to expand this in powers of z. And the expansion will be valid if you put it in the form of powers of z, okay? The expansion will be only valid if this series converges. Clear? So for that matter, if you look at, so you are having branch points of this very function. Okay, so these are at where? Plus minus I, where the function goes to 0. Clear? Samashya?
Yes.
Okay. So let's look at, so let's plot it. So you are having this kind of situation. So this is your I and this is your minus I. What is the radius of, so this is your, these are your branch points. So this, the branch cut arises here and the branch cut arises here. So what is the radius of convergence? So when mod of z is less than 1. So that means it exists within this very unit circle. So this is your radius of convergence, or this is the circle of convergence, region of convergence. Okay, so it exists when mod of z is less than 1. So if mod of z is greater than 1, then it is not convergent. Clear? So I can say you are having convergence only. Okay, so this implies convergence. So then you can write this f of z, okay, is equal to 1 plus z square plus 1. Okay, 1 by 2, huh? Z square by 2 and so on. Clear? Everybody got it? Okay, so you can only have a convergence within this very factor. Now look at this, you are having the same situation arising here. So that means this very function is having branch points where? At plus minus I. Clear? So you can consider this as z. Okay, when this value is equal to plus minus I, you are having the branch points. Clear? And within the, okay, so if the magnitude of this very object is less than 1, then you can have a convergence of this very series. Clear? Otherwise, it is a divergent series. Everybody followed it?
Yes.
Okay, so we can have convergence. Okay, so the convergence will be like this in lambda mod of v squared, sorry, mod of v by half of e1 naught minus e2 naught. Okay, so this should be less than 1. So now you have got actually the condition for the perturbation to be valid. So that means the perturbation theory is valid only within this region, within the region of convergence. Okay? Got it? Okay. So it means you are having this lambda magnitude of v, it should be less than half of e1 naught minus e2 naught. Okay? So if this condition is satisfied, then the perturbation theory is valid. So this gives you actually, if you see, now this gives you actually the magnitude of how small this perturbation should be. Clear? So last time we only qualitatively said what, okay, so this perturbation Hamiltonian should be small. Clear? Now here we have quantified it for a two-level system, how small it should be. Clear? Okay, so this is the smallness of the perturbation. Then you can calculate these energy levels. Okay, so E plus you can see, so it will be, let's say, E1 0 minus some okay, so one will be up and another will be down. So you will be having some lambda square, okay, mod of v square divided by something E1 naught minus E2 naught kind of thing, okay. and then you are having this E minus, so that will be some, okay, so E2, I have written wrong, so let's take this as E2, so it will be, sorry, E2 plus, and this will be E1 minus, so minus lambda square mod of E square divided by like this. So what it means, so you are having, these are the two levels. Okay, so one level, E1 will get shifted down, and you are having actually the second order correction. Huh?
Yes, sir.
Okay, so you just need to expand that this square root of 1 plus this factor. Huh? So in power series, and then calculate. One level will be actually, it will get shifted down by how much? By this much. It is a small quantity, another will go up. Okay? So
Yes.
when you turn off the, let's say when you turn off the perturbation, let's take lambda tends to 0, what you will get? So you will get back the levels. Clear? Okay, when you put lambda equal to 1, so that means perturbation is full. Okay, so you are having the complete perturbing this part, and they will get shifted up and down. Clear? Okay? Okay. So now let's have certain remarks on this thing, then we'll go to the certain examples. So let's have remarks on this perturbation failure. Certain remarks, let's go. Okay, so the first thing is when you are having the degeneracy, it is not valid. Eh? The first remark. Okay, so what is your second order correction? Okay, so what is your second order correction to the energy? Okay, so let me give the corresponding. So it's something minus. Okay, and not equal to m, then you are having n at r1 mod of m square divided by. Okay, so this is the second order correction. So here it will be some it will be more apparent. So now let's say if these are actually sorry, n naught. So these are the unperturbed states. Now if there is a degeneracy, clear? So let's say, what does that mean? Okay, degeneracy means if you are having two or more than two levels having the same energy, clear? So we are having degeneracy. Now let's say if you are having n naught and m naught, they are having the same energy, clear? So what will happen to this thing? This goes to 0. So then in case of degeneracy, this blows up. Oh, okay? It blows up. Okay, so that means this is not a valid kind of thing. Okay, or in other words, this is not a valid formula to calculate the second order correction in case of degeneracy. So in case of degeneracy, we need to look for a different method to solve a given problem. Clear? Okay, so I cannot directly apply these formulas to the degenerate case. Okay, so those we are taking in a moment. Clear? Okay, so now let's look at the second remark. Okay, so let me write. Okay, first order correction to the energy. Overstates ground state energy. So what does that mean? Okay, so let me have an exactly solvable model at hand. Clear? Let's say I am having a harmonic oscillator. I know its eigenstates, all that. Now let me add the perturbation and calculate the energy correction. What does this statement mean? So I'll be having the when I add the first order correction of the energy to the ground state, so my energy will be greater than the ground state energy. Clear? So it comes actually from a principle, the principle what we are going to study, the variational principle. Variational principle always overstates the ground state energy. Okay? Okay, so let me write it. Okay, so let's prove this very statement.
सर ये तो 0 n0 h1 m0 आपने लिखा है 0.
No. So this will go to 0. So when there is a degeneracy, so En0 and Em0 will be same. I am saying N0 and M0 they are degenerate. Clear? So when they are degenerate, their energy is same. Okay. So this is the energy corresponding to the unperturbed states M0. This is the energy corresponding to the unperturbed states M0. When they are having the same energy, what will happen to this thing? This will become 0. So that means this blows up. And it may also happen, this will also go to 0. So you will be having a 0 by 0 form. Clear? Got it?
Yes.
So let's prove this very statement. Okay. So let's consider the ground state. It is 0. Okay? So what is the, okay. So let's consider its energy to be E0. Clear? So you'll understand it in a moment what I'm exactly saying. Yeah? Okay. Okay. So our Hamiltonian with perturbation H lambda at something H0 plus lambda H1. Okay. So let's calculate the this objective 0 H of lambda 0. So that's equal to okay 0 H0 0 plus lambda 0 H1 and 0. Okay, so what this object is? So this is your E0, clear? And plus lambda the 0 H1 0. Okay, so and I can write this thing as, so you can expand this thing, I can write it simply as E0 plus some first order correction lambda E1 plus order of lambda square. Okay, so this will be the correction. Clear? Okay, so by variational principle we say this we are going to study. Okay, so variational principle always overstates the ground state energy. Okay, variational, okay, let me give a gist of that. Suppose if I am giving you the Hamiltonian and you make a trial wave function. You take an arbitrary wave function and calculate the energy corresponding to the wave function and then see whether it matches your ground state or not. Clear? And then you iterate it again. Okay? And then calculate, okay, obtain a new trial wave function and look at whether it is a ground state or not. Okay, until it reaches to the ground state. It is some, okay, so you are starting with some trial wave function. Okay, and or let me put it this way, you are starting with, you guess with a wave function for a given Hamiltonian and calculate the energy. And then correct that very wave function and look for the energy again. Okay, until and unless you reach to a given point of your accuracy. Up to what accuracy you get the ground state energy. Okay, and that energy will be always greater than the ground state energy. So what does that mean? So it means this energy, okay, so you get actually an energy here. Okay, so is this the energy? So this is the ground state energy, clear? And this is, okay, so if I take the variational principle, this energy will be always greater than this E0. Clear? Okay, so now if you see, so what this object is, so you are having, so let's take up to the first order correction. So this object is lambda E1, so what this is equal to, so E0, it is. So that means this very, the first order correction overstates the ground state energy. Clear? That is the statement what I wrote. Okay, so that means it will simply increase the ground state energy. Okay, so okay. So only in case of, let's say if you put no perturbation lambda equal to 0, then E0 is same as E0. Clear? When lambda is equal to 1, then this is a larger quantity than E0. Okay, so this is very important quantity. Okay, so let's look at the second order correction. What it has an impact on the second order correction. So let's calculate the second order correction on the ground state energy on ground state. Okay, so what is our ground state? This 0. Okay, So this will be the second order correction. 0 means ground state and it is second order correction. That's equal to, let me write the formula. So it is minus, okay, summation m not equal to 0. It will be something 0 hi m, okay, like this, em0 minus e0 of 0. Because here n is what? Okay, so let me write put m naught. So n naught is here the ground state, clear? And m naught are the intermediate states, clear? So it is m naught comes from, it is this formula. So if somebody is having the problem, 0 h1 m naught, okay, m naught h1 em naught minus, clear? Okay, got it?
Yes, sir.
Okay, so now let's look at this very objective. So what is second order correction gives? Okay, now look here. So this m is not equal to 0. Since I am taking 0 is the ground state, clear? So m is not equal to 0. That means this em is always greater than e naught. Okay, so here I am having this em naught. It is always greater than e naught. Clear? So by that very argument. So this em may contain the corrections, but that is always what? Greater than. So this is a positive quantity. And since this is a mod square, this is also what? A positive quantity. It means second order correction is always negative. Clear? Correction is always negative for ground state. It should be remembered. For ground state, it's always what? Negative. What does that mean? So it means the ground state will be, okay, so there will be the lower energy of the ground state. Okay? When you add the second order correction energy to the ground state, you lower down its energy. Clear? But what is doing the first order correction? It is increasing. Clear? But the second order correction is lowering down. Clear? Okay. So in other words, so you always calculate the second order correction to the energies to understand the stability of the problem. Okay? Okay. So now let's expand this very formula. Okay, for any level, let's consider you are having some nth level. Let's calculate the second order correction to this level m. Clear? Okay, now that is for the ground state. For any level, let's calculate it. Okay, so what it will is, so let me write summation m naught equal to n. So I'll be having n h1, okay, m naught like this, m naught hi n naught by em naught minus yes. So this is the second order correction. Clear? Okay, so let's take, since m is not equal to n, so let me take this very level. So while m is equal to n, so that very level, huh? And we are not considering m equal to n level in this very formula, is it? So you will be having all the levels. So these are the levels for which, okay, so m is greater than n, and these are the levels for which, okay, m is less than n. Now let's separate out this formula, okay? Let's expand this formula for the terms where m is greater than n, where m is less than n. So that means you have to simply put it into two terms, where m is less. Okay, so let's put it. So this will be simply equal to minus summation m less than n. Okay? Clear? Okay. So that will be n naught h1 m naught h1 n naught divided by em naught minus en naught. Clear? Then you will be having a term m greater than n. Okay, so these are the only two terms you will be having. So n naught, the same thing here. Okay, so you are having em naught minus. Okay, so now let's look at this very thing. So since m is less than n, okay, let's look at the denominator. When m is less than n, that means this object is negative. Clear? So you are having minus, and minus that will become plus. Okay. So you are having here summation m less than n. Okay. So it will be simply magnitude of m naught h1 m naught mod square. Let me put in now compact way. So m naught minus n naught. Now this is a positive quantity. Clear? So m is positive. Okay. Sorry. This is now. So let me write it now this way: en naught and em naught. Now this becomes positive. Huh? I have simply put en first to take this minus out. Huh? Clear? Okay. And what is the other term? So you are having minus. Now since m is greater than n, so this is positive quantity already. This is positive. So you will be having a minus sign. So m greater than n, magnitude of n naught h1 m naught mod square by em naught minus em. Okay. So now let's interpret these things. So you are having the terms for which m is less than n. So they increase in energy. Is it? So forget about the second term. So you are having this as a negative term. Clear? Clear? When energy is negative, what does that mean? So there is actually the push towards a certain level. Clear? So when energy is positive, there is some sort of repulsion. Clear? So in other words, for m less than n, so these very levels will push this level up. Clear? So there is some sort of repulsion and attraction between the levels. Okay? So it comes from the second order correction. So in other words, m less than n, so the term is positive. Clear? Okay, so in other words, these levels will actually push up this up. Push this level up. This m equal to n level. Clear? Since we are looking for the perturbation for which level? Nth level. Clear? Got it? So the effect of the second order perturbation is certain levels will actually push this up and other levels will push it down. Clear? Got it? So in other words, there is some sort of repulsion and attraction between the levels, or some repulsive behavior is existing. Okay, second order correction gives us that behavior. Okay? Okay. So let's take an example. So let's take the Stark effect on the ground state. Okay. So what is Stark effect? So it is simply the splitting of the energy lines, splitting of energy levels in presence of electric field. So if you are having a static, okay, so any kind of electric field, whether it is static or the time varying electric field, so if there are splitting of the energy levels, we call it as a Stark effect. Okay? Okay. So we will consider the Stark effect on the ground state of the hydrogen atom. Clear? Okay. So let's take, suppose you are having a charge distribution. Some sort of, okay, so let's take some charge distribution where you are having positive and negative, they are equal. Okay, so let's intuitively understand this kind of thing. Okay? So if you put this kind of distribution in the electric field, what will happen? You put some charged body in the electric field, what will happen? So there occurs polarization. And you quantify that polarization in terms of the polarizability of the material. Clear? Okay, great. Now if you are having a spherically charged distribution, let's think of the ground state of the hydrogen atom. That is spherically symmetric object. Clear? Yes, so charge distribution is spherically symmetric. Clear? So now let's put that state into the electric field. You apply the electric field. Okay? So what should happen? Okay, tell me what should happen. So there should arise some polarization. Okay, and we will look. Okay, so whether there the polarization occurs at the first order correction or second order or at the higher order. Clear? So it's not okay. If I put it in the weak electric field, so it is not necessarily there will occur the polarization, is it? Because it does not contain the permanent dipole moment. Permanent dipole moment here is 0. Clear? Okay, so let's go to the hydrogen atom. Okay. Okay. So let's take the hydrogen atom. So what is our ML today? P square by 2m plus some V0 of R. So what is V0 of R? It's minus E square by or minus E by R. Minus E by R. It's Q by R. Huh? So this is your Coulomb potential. Huh? Okay. And let's add the perturbation. Okay, so let me write. So this is your H0. Okay, so first discuss this H0. So what is the ground state? You cannot apply the, okay, so there is another point. So this non-degenerate perturbation you can apply only to the ground state of the hydrogen atom, because there is no degeneracy in the ground state. You are having only one level. Now if you have to apply, let's say, calculate the Stark effect on, let's say, second level. So how many levels are there? There are 4 levels which are degenerate. 2s, 2px, 2py, 2pz. So those 4 levels are degenerate, and you cannot apply the same formula there. Clear? And we have to rely on certain degenerate perturbation. So that we'll be doing. Okay. So what is our ground state? Okay. What is the ground state here? Okay. Tell me, what is the general state of the hydrogen atom? So it is described by NLM. So let's say this is the unperturbed state, and I will denote it by some cat K0. K0 describes this NLM. So unperturbed state. Or K, let me write. Okay, some K0, unperturbed. Okay, so let me not write. So this is your unperturbed state NLM. Okay. So what is our ground state? So that will be simply n is equal to 1, L equal to 0, and M equal to 0. So let's define this state by some K0. Okay, so this makes sense. So we will be looking the effect of the perturbation on this very state. So let's consider our electric field like this thing, minus E, okay, magnitude of the electric field, and let's put the electric field in the Z direction. Clear? And if you look in the spherical polar coordinates, Z is equal to R cosine of theta. Okay? Got it?
Yes.
Okay, so this Z is small, or the magnitude of the field is small. Now the point is here, this Z does not go to minus infinity. Why? So if Z goes to the minus infinity, so what you are having, this is a positive, this will become a positive quantity, it will become very strong. Okay? So in that case, the bound states which are already there, they can become unbound. Clear? So we are not considering that kind of situation. And we are considering actually the limited values of the Z. Okay? Because you consider, let's say, hydrogen atom, so Z will be within the limits of that orbital. Huh? Clear? Within that very domain. Okay. So let's write therefore. So what is our H? H is simply equal to H0 plus lambda H1. Okay, so let's calculate the first order correction to the energy. E0. 0 means the ground state. Clear? So let's calculate its first order correction. What is that equal to? So it will be simply K0, H1 and Kp. Clear? So I am using K0 in just to differentiate between these indices, NLM. Okay? So what is that? What is our K0? So it is 1, 0, 0. So H1 is simply, okay, so let's write it, minus E, magnitude of E, okay, 1, 0, 0, Z, 0. Okay, so this is our expected, it is the expectation value of Z, is it? So can anyone tell me what this expectation value is? Can anyone tell me? I have given you the hint earlier. What is expectation values? Okay, so let me give this idea. So what is your dipole moment? It is charge into distance. Clear? So let's write Q into R. Clear? Distance of separation between two charge centers. Is it? So in other words, so what this E times Z will represent? So if I write it, okay, Q is a number, is it? And R is, when you quantize it, so R will become simply an operator, position operator. Clear? So you will be having this will go as a dipole moment operator as Q and R. Clear? Solution? So now let's look at E and Z. So what it will go as? E and Z. Because we are dealing with the quantum mechanics. Clear? So it's a quantum mechanical problem. What this will give me? Simply, it is a dipole operator. Clear? It will simply measure the dipole moment in a given state. Clear? So in other words, this expectation value, you can think it as minus magnitude of E. Okay, 1, 0, 0. Okay, so the expectation value of this object. Clear? I have put caps just for you people. Huh? So it is the expectation value of the dipole operator. Huh? So what should it give me? Dipole moment. So your S orbital is spherically symmetric. Is it? So what is the dipole moment? Because it does not possess permanent dipole moment is 0. Okay? So this is one way to understand it. Another way, from the mathematical point of view, okay, since you can write this very object minus E magnitude of E like this thing, D3 of R. So this is simply the expectation value of Z. Eh? Okay, so you can write it like this thing, psi star 100 R and Z psi 100 R. Okay, so psi 100, it is the ground state. Clear? And ground state, okay, so you can write it as minus E magnitude of E D3R Z mod 100 square. Clear? Okay, so the ground state of the hydrogen atom possesses even parity. Clear? And this is having odd parity. Odd and even, the integration over the entire space yields you 0. Clear? Okay, so by that argument, so this again 0. Or if you are not able to understand it directly, okay, so the dipole moment does not connect, so this Z operator does not connect the same states. Got it? So it does not connect. So you are having this state and this state. So you have done selection rules? Huh? Okay, forget that. Okay. So just do it. What is your psi 100? Just do this integral. Psi 100 is root of 2 pi a cube e raised to minus r by a. Clear? A is the Bohr radius. Okay? So just take this very thing. And what is Z? Z is equal to r cosine of theta. So you integrate this over phi, then theta, then over r, you will get this equal to 0. Clear? समझ आया? So that means there is no correction to the ground state. Clear? Sorry, there is no first order correction. Huh? There is no first order correction. Now let's look at the second order correction to this very problem. Okay, so what is our second order correction? So let's calculate the second order correction to the ground state. That is summation. Okay, summation. Let me write K not equal to 0. That means it does not belong to the ground state. So you are having like this thing. K naught Hi 0 mod square divided by EK0 minus E0. Clear? Got it? Okay. So this is a very complicated formula to evaluate for the hydrogen atom. Okay, so now what I will do, simply use H1. What is H1? E Z. Okay, so what are the numbers? Charge and electric field. These are the numbers, they will come out of this everything. So I will write it as, so it will be minus E square magnitude of this E square, like this thing. K naught equal to 0. Okay, so you are having K naught H1 0 more, sorry, it will be Z like this, Z square divided by Ek naught minus E naught naught. Clear? So that will, you can see this is non-zero quantity. I will give you an estimate of this very thing. How? Okay, its value and estimation. We cannot calculate it exactly. Just an estimation we can do it. So now you can see. Okay, so you are having, this is the second order correction to the energy. So that means at the second order you are having the splitting of the levels or the dipole. It is not the permanent dipole. It is something induced dipole moment arises only at the second order correction. Clear? Because if the energy correction is non-zero, it means there is a splitting of the level. So that means that you are inducing actually what? Charge centers, positive and the negative charge centers. Clear? Okay. So then if you are making the polarization of the first state, so you have to define what? Polarizability. Clear? Got my point? So samajh aa? Are you getting it?
Yes, sir.
So what I am saying, so what I have done here, since the second order correction energy is non-zero, is it? So what I have done actually, so your first orbital is where? In the electric field. Clear? 1s state is in the electric field. What has happened then? So there is a polarization. Okay? Some sort of polarization exists. It does not exist at the first order, but it exists where? At the second order. Okay? Clear? So if you are having a polarization, what you need to define now? A polarizability. So you have to now define the polarizability of the ground state of the hydrogen atom. Clear? Okay, so how to define that? So I will write it as like this thing. E02, so this I will write, okay, alpha. So let's call alpha to be the polarization of the state, 1s state, or the polarizability of the ground state. And so, okay, so alpha gives you the polarizability of 1s state of hydrogen. Clear? So now, what is this alpha now equal to? So let me write half. So it is half. Okay. So let me write it half. So what will be then alpha? Now tell me, compare the two. What will be the alpha? Just compare. Huh? Just compare. Yes. Okay, so it will be, so alpha is equal to minus twice e square summation k not equal to 0, okay, k, okay, z, and you are having, okay, so I should have, so what is this 0? It is the ground state, so I should have put 1 0 0, I should have put 1 0 0. So there is a notational problem I have done. I have done a notational problem because I have done ground state by K0, if you remember it. Is it? K0 I have done the ground state. So let's write them. Okay, so let's write it simply as K. Call this as simply K. Okay. So let's call this as M0. Okay, so let's call this as K0. Okay, where N is not equal to K0. So it will be simply K0. Okay. So because I have done the notation in this way, so I should not have done. Okay. M is not equal to K0. Clear? Got it? Okay. So this is the, okay. So let's write this polarizability. M is not equal to K0. Okay. You are having M0. So it is K0 mod square. So this is your, okay. So this is the ground, so you can put a K0 here as well. Okay, you can put K0 here as well. K0. Clear? So now this is your polarizability. Okay, so we need to calculate, okay, so let's calculate its upper limit. So a rough estimate of this very formula. It is actually very complicated. You can see it from, because it is actually sum over all possible states. How many states are there? Infinite number of states. And you are excluding only the ground state. And sum is over rest of the states. And this very sum is very complicated because you need to calculate these very objects. And then you have to calculate this, these integrals as well. Clear? So let's get the rough estimate of this very formula. Clear? Samajh aaga? Okay, so how to do it? So let's assume, okay, so let's put a rough estimate. Okay, so let's assume this very object is constant for the time being. Okay, then we will see here. So we'll put a limit on this object. Clear? Okay. Okay. No, okay. So let me write it this way. So instead of doing that way. Okay. So let's look at this thing. So Ek is any kth level. Clear? And this is only the ground state. Clear? So I am having. So you can absorb that negative here. So you can write like this thing minus. Okay. So minus E naught. So that means corresponding to the ground state energy plus the energy Ek naught. Clear? What is this energy? It is for any level K. Clear? So what this is equal to? So this is greater than minus E naught, okay, plus let's say the first level. Is it okay? Okay, so that means, so this very object is always greater than this very object. Clear? So now you can see how. Let's put K equal to 1, then it's equal. Huh? So if you put K equal to 1, then it's equal. So let's, okay, so let's have greater or equal. Let's put K equal to 2. What is the gap? For K equal to 2, what is the energy gap? Okay, look at the first state. It is 13.6 electron volt, is it? So what is for the second state? First excited state, how much is that? You divide by 4, is it? So it is about 3.4. What is for the n equal to 2 level? Sorry, n equal to 3, I should say. It's divided by 9. How much is that? It's very small. Clear? So that means, let's say, this difference is what? This difference is very large. Is it? Then this difference. Clear? So, or if you make any kind of pairs, okay, so then you can see, so the difference is becoming smaller and smaller as you move away from the first state. Clear? Got it? Okay, so that means I can have this alpha. Okay, so this I can write less than, okay, this way, less or equal to, because this is in the denominator, is it? This is in the denominator. When I take 1 divided by this thing, then 1 divided by this thing is larger than this thing. Okay. Clear? Okay. So, okay, so in that case I can take, okay, so am I saying correct? Am I saying correct or am I saying huh? Okay, so am I saying correct? Huh? So what I have said, are these things correct or wrong? So I should have put it this way. So there is a problem in defining. So I should have put a minus sign here, okay? And you are having the plus sign here. So you are having a plus sign like this. It's not correct. Okay? So now it makes sense. So it will be something twice E square, okay, divided by magnitude of this thing, Ek naught minus, okay, Ek naught 0. Okay, so if you take the magnitude of this very formula, okay, so let's take the magnitude of this thing, it will be the magnitude of this thing. Clear? Okay, so since you take the magnitude, so this is very small, okay, so I'll write it like this way. So what I have done, so it is simply E1 naught, right? Clear? So by this very formula, so it is summation M naught equal to K naught, okay, magnitude of M naught. Everybody has followed it? Okay, so I am giving you a rough estimate of this very object. Now you can calculate how much is this thing. So what is your ground state energy? Anybody? What is the ground state energy? How much is that? E square divided by, so in these Rydberg units, how much is that? E square by twice A naught, right? Twice A minus, what is this, right? E square by 8A. So It is in the Readberg unit, sir. You have done this, sir. Okay. So how much is that? So it will be e square 6e square divided by 16a. So how? So when you say 3e square divided by 8. So this is the difference. Okay. So now let's calculate that sum. So that's very important. Look, why I have put a negative sign. You should not be, surprised, because second order correction lowers down the ground state energy, is it? That's why I have put a negative sign. And alpha is it's a polarizability, it's a positive quantity. Eh? So we will calculate it's a positive quantity here. Clear? So that's why I absorbed that. Okay, so I kept this negative sign here and put it here. Eh? This alpha, define it in that way. Clear? Got it? Okay, so now let's calculate that sum. Okay, so what is this sum? Summation m naught equal to k naught. Okay, so it is m naught z k naught. Okay, so it is like this thing, k naught z. That very sum. Okay, so this I can write like this way: summation m naught equal to k naught. Okay, I will put this very factor first, k naught z m naught, okay, m naught z. Okay, so what is your k naught? That is 100 state. Okay, so I will put it like this thing, 100 state z. I will take this summation inside. So it is summation m naught equal to the ground state. So let's call that 0. Huh? Okay, so let's call that as 0. You can call it as a k naught. So it is m naught, because sum is only over m, is it? Okay, so I'll put it this way, and then you are having z, and k naught is 100. Clear? Got it? And which state is not available in this very sum? Only one state. That is the ground state is not included in this thing. And we know, since the eigen states of a given of the hydrogen atom are complete. Clear? So what does that mean? You are having this very objective m goes from 0 to infinity. Okay, summation of m naught. So this is equal to identity. Clear? All the states. 0 means from the ground state. Okay, so what is ground state? I am calling as the k naught. Okay, so that means let's put the 0 states separate. So this sum I can write 100 plus all the rest of the states. M naught equal to this k naught up to infinity. So I have taken out this way. Okay, you just using the completeness condition. So that means this very sum I can write as 1 minus this object. Clear? So I should not put it full. So this is implies. So it means this very sum I can write as so I am using now this sum I can write. So this objective it's equal to 100 z. Here I will write as 1 minus this 100. Okay, z and 10. Clear? Using that very formula. Huh? Okay. So now, so what I will write it as 100. So you are having z square 100 minus 100 z 100 z and 100. Now we have just shown this is equal to 0. So what remains there? Only this object. So that means this is simply equal to the expectation value of z square. Okay, that very sum is simply equal to the expectation value of z square. Now for the hydrogen atom you have done probably, okay, for spherically symmetric, for one state, for the ground state in the hydrogen atom, you are having this x square, it's equal to y square, that's equal to z square, that's equal to 1 by 3 r square. Okay, this means it is for one state of hydrogen. Clear? therefore I can write this z square, okay, as 1 by 3 r square. It will be simply equal to d3r r square mod psi 100 r square. And you calculate it, it will be simply equal to a square. A is the Bohr radius, eh? So r square will be simply equal to Bohr radius square. Clear? So now let's use, therefore, the polarizability, therefore that alpha is less or equal to, okay, so we have calculated the upper bound, okay, so what is that equal to? You are having, what was that? E square divided by that very factor, so how much was that? 3 e square by 8 a multiplied by this a square. So, and there is one more factor, there is 2, okay, twice e, so it is simply equal to 16 a cube by 3. Okay, so how much is that? 5 point. So, okay, 16 by 3 a cube. Huh? So therefore, so this is the polarizability of the, this is the upper value of the polarizability of the 1s state of the hydrogen atom. Clear? Got it? Okay, so you can now write the energy difference between the first and the second, okay, second order correction, ground state and the second order correction. So let's define this delta K as the energy difference between the perturbed, so this is the perturbed Ek minus Ek naught. Clear? So what is the unperturbed energy? And this is the for the full Hamiltonian, including the perturbation. So let's calculate the second order correction. Delta 2, okay, let's say the delta 0 for the ground state. So it will be simply what? What it will be? Second order correction. Okay? So it will be simply E0 minus E0, 0. So how much is that? So that is simply equal to minus 1 by 2. So minus or plus? Positive. 1 by 2 alpha magnitude of E square. Difference it is negative. Now like E0 is what? So this, yeah or not? So you are having this E0 equal to E0 of 0 minus lambda square E, okay, so plus lambda E01 plus lambda square E02. Clear? So what is this thing? So E0, 0. So this is 0 and this, when put lambda equal to 1, this is minus 1 by 2 alpha magnitude of E square. Clear? So what is that therefore? Delta 0. The difference between the two. It is. Okay? So therefore the gap between the splitting of the levels will simply depend on the polarizability. Yeah? Okay? So or in other words, we can calculate what is the polarizability. Okay, suppose how you know this is the correct polarizability. Clear? So you simply put hydrogen atom in some electric field, okay, and you measure what is the, you calculate or you look at the spectrum of the hydrogen atom. There you will find the splitting of the levels. Clear? And you calculate how much gap is there. Huh? So this is the energy gap between the splitting. Clear? Okay, so let's say if you are having this 0 state and this will be the splitting of this thing. So you calculate this much of gap, okay? And you know this is the externally adjusted electric field. Clear? From there you can calculate what? Polarizability. So this is how you measure it. Okay? So is time over? So let's take degenerate perturbation tomorrow. So class from tomorrow is at 9:30. So you come.